As I mentioned, my background's aerospace engineering. I've designed missiles, aircraft, race cars, all that good stuff. Batteries are really complex.
Hi, I'm Onas Bolton, founder and CEO of Octet Scientific.
And I'm Emily Dickens, Chief Commercial Officer at Octet Scientific.
And welcome to Aqueous Energy, the show where we talk to the pioneers shaping the future of aqueous battery technology.
Today, our guest is Michael Burz, CEO, President, and co-founder of rechargeable zinc anode firm Enzinc.
Our show met Michael at Enzinc's Manufacturing Technology Center in Oakland, California, for a conversation about how the company's zinc sponge technology, which they licensed from the U.S. Navy, is making aqueous batteries more competitive with lithium ion, and how they solved a dendrite conundrum that even Thomas Edison couldn't crack. Plus, we'll cover Enzinc's unique approach to parallel path manufacturing and R&D, and what that means for fast scale-up and lots more.
You'll also see a golf cart that could spell a major shift in urban e-mobility. Let's go to the conversation. Welcome, Mike.
Oh, thank you, Emily. It's a real pleasure. Just some quick background for your audience. I'm the co-founder and CEO of the company. Background is aerospace and automotive engineering, having designed missiles and spacecraft and race cars, etc. But we decided to kind of turn our attention to renewable energy. And we'll talk about kind of how we got into this. But yeah, I'm sitting here at our Manufacturing Technology Center in Oakland, California. We do have another facility up in Richmond, California, which is engineering R&D. But behind me then is kind of where we're making some of the zinc anodes that we'll be discussing and the zinc technology in this session.
Well, let's start maybe just with the background of Enzinc.
Wow. Like a lot of battery technologies, this does not happen overnight. We hope that sometime in the future will be considered like a 25-year overnight success. That'll be fun because it does take a lot of time, a lot of energy and money to go bring a new battery, into the marketplace. So the story actually starts way back in 2011, 2012. When we were introduced to the U.S. Naval Research Laboratory in Washington, D.C. And one of the academics that we were working with at UCLA recommended that we talk to Dr. Deborah Rollinson and her team at the U.S. Naval Research Laboratory that was working on an alternative to lithium batteries. So trying to make a short story, the Navy was interested in replacing their lead acid batteries that they've been using for over 100 years. But they recognized as the Navy was moving into a more digital Navy, they needed more energy storage that had higher energy density and didn't take up so much room aboard ships and particularly submarines. So they took a look at lithium, like most people do, had a rather bad experience with lithium. It's not that they're going to get rid of lithium, but for the application, they thought fires are bad. So particularly aboard, naval vessels. So they tasked the Office of Naval Research, tasked the U.S. Naval Research Laboratory to investigate a battery chemistry which had the energy of a lithium battery, but was as robust and as safe as the lead acid batteries the Navy's been using. And that led them under Deborah Rollinson's leadership, because she's kind of an expert in things like foams and sponges. Aerogel is one of her things. She's head of the electrochemistry division. They took a look at zinc, which interestingly enough was, as everybody knows, originally done by Thomas Edison, who also happens to be one of the founders of the U.S. Naval Research Laboratory, which I thought was wonderfully coincidental. But they took a look at it and said, zinc would be really cool, but there's several issues with it, regarding its energy density and dendrite growth. And so using their background in electrochemistry and sponge technology, the Navy postulated, could we make a zinc metal sponge? And we were looking at alternative chemistries as well. That's how we got introduced to Deborah. We were kind of the engineering guys. They were the scientists. So we provided kind of requirements. They required, the technology. We then joined together for an ARPA-E award. And this is way back in 2013. We were selected for this. It's called Robust, Affordable, Next Generation Energy Storage. That led to a program between 2014 and 2015 to demonstrate that this zinc sponge does what the Navy was looking for. And that's how kind of we got started. So we worked with them on that ARPA-E award. Then they were able to get the patents, and then we were able to get the license. And once we got the license, we were able to raise money, and here we are.
Great. Yeah, thank you for that background. Very interesting. Going back to the history of zinc batteries, you mentioned Thomas Edison has used these. So why are they not more available today?
Oh, well, I mean, zinc batteries are, right? A lot of alkaline batteries are zinc based. The ever popular hearing aid battery is usually a zinc air battery. The issue was they weren't rechargeable. And way back in the early 1900s and all the way through the 1950s, rechargeable batteries weren't a big thing, for electronic devices and so on, for cars. So, in fact, it turns out that the largest lead acid is the largest rechargeable battery. In fact, it still is by quantity in the world. It just turns out that because of this dendrite growth, this stalactite type formation that forms in charge and discharge is what kills, the zinc battery. And unfortunately, they grow really quickly in zinc. And so poor old Thomas Edison, who didn't have access to a scanning electron microscope, couldn't really see what was happening so quickly. And the batteries would just die after, like a couple of dozen cycles. And of course, if lead acid is doing, 300 to 500 cycles, then in the marketplace, it didn't make much sense. But in the 80s, people started to take a look at alternative chemistries, something better than lead acid. Nickel metal hydride, nickel cad were on the scene, and people said, oh, let's look at zinc as well. Let's resurrect it. And research was pretty significant. And what people were able to figure out is how to slow dendrites down, but not eliminate them. So progress was being made. But in the early 90s, along came Dr. John Goodenough and the fabulous lithium battery, and it completely overshadowed anything because at the time, zinc batteries were around 60 watt hours per kilogram. And for reference, like lead acid is around 30 watt hours per kilogram. And the first lithium batteries were like 90. And so here was a battery which is 3 times lead acid, and you could pack it, all that energy into a small thing so you could have a laptop. And basically interest in zinc kind of faded. And so lithium became predominant. But I think that that's kind of changing as people realize that a lithium battery is not the end all be all batteries for everything, even though the lithium industry would like you to believe that to be true.
Yes.
Yeah. Well, in your opinion, what are the limitations of lithium ion that you see?
I will try and say this so I don't get in trouble. The first one would be, of course, in supply chain. As we all know, we've read about this, and it's a true statement that the Chinese invested a lot in battery material processing and manufacturing. And so 80 to 90% of both the materials used in a lithium battery as well as the processing and the manufacture is all done in China. And because of their very, very efficient supply chain, plus the fact that they don't have some of the regulations around environmentals, they become extremely cost effective. So there's that from the economic side. On the technical side, some of the issues that we find in some of the applications, particularly around power density and float charge, where you need to keep a battery, continuously charged for instantaneous operation, lithium is not all that great at doing that. And then, of course, there's the other two issues, which is thermal. One is temperature range, and people are working on that. But because it's an organic electrolyte, the low temperature and the high temperature ranges are somewhat constrained compared to an aqueous or water-based battery electrolyte. The temperature ranges are much greater. And what that means is if you're going to use it where it's really, really cold or really, really hot, that means you have to have an additional subsystem to protect those batteries from getting too cold or too hot. And that's just added systems. And as engineers, we know once you start adding more and more systems, your mean time between failure for system operation, gets shorter and shorter. And that's, of course, dollars, right? You've got to add dollars to that. And then, of course, the other one, which is the ever popular thermal runaway. And because if you're going to, pack all that energy into a little tiny space, you have to have incredible manufacturing quality, which people have achieved, but that comes at a cost in terms of the number of batteries that are acceptable, your yield rate. And so you have to be able to make sure that those batteries don't catch fire, particularly in a mission critical application, which means now you have to layer on more protection. And there's just a lot of money being spent for lithium batteries to take over some of those disadvantages. Like a lot of research, a lot of money, and that just ends up in a systems cost, which has to take into account not just the battery, but the packaging, the thermal management, and the fire protection. So those are some of the disadvantages that, frankly, zinc batteries don't have. The zinc sponge is a metal sponge. What we do is we take a bunch of zinc particles and we center them together to form this zinc sponge structure. And what happens with it, why it's so effective, is that it's this random interconnected structure in which, as the battery discharges, the zinc moves from zinc to zinc oxide, and then when it charges, it moves from zinc oxide back to zinc. But that oxidation takes place only on the external surface of the sponge, which means that the internal structure is still pure zinc and can carry a current. That means there is no time that you end up with the charging current being impeded. That's what forms dendrites, is that you tend to isolate the particles from one another because they all get coated in zinc oxide. And so what happens is the current goes through smaller and smaller pathways, and therefore you get hot spots and it generates dendrite growth. By having a continuously wired interconnected zinc structure, there is always a path, and therefore there is no dendrite growth. And then once again, because it's a sponge, and think of it like the sponge on your kitchen sink, but at the micron scale, it has a very, very high surface area. And all of that surface area then is reactive.
I know that you've described your batteries, your approach, or Enzinc's approach, as to being cathode agnostic. And I think what you guys are doing is quite a bit different than some of the others we've talked with who are maybe making the whole battery. So could you explain a little bit about your kind of business model and how what you're doing can be cathode agnostic? Sure.
So the cathode agnostic part comes because of the technology itself. To get the performance that the Navy was looking for, we ended up with this metal sponge. And it has three attributes. The first is that the sponge structure eliminates dendrite growth. It doesn't suppress it. So we've already gone like 1,000 cycles at 100% depth of discharge with no dendrite growth. Big advantage, right? The second part is that because we have a sponge structure, we have a higher usable surface area, reactant surface area. So we get about 2 times the energy density of other zinc batteries. And because it's just the zinc structure that gives this performance, we are not tied to any particular cathode. So we're starting with nickel because it's well characterized. We can get to market quickly with it. but we don't use additives to try and get rid of the dendrites. As you guys know, we're using it for, gas evolution, minimization, etc. And we don't use mechanical systems, right? We don't have to have flow battery kind of things to achieve the energy density or the cycle life. We don't have to worry about mechanical systems either pumping stuff around or scraping stuff off or whatever. It's just the anode itself. So that means that we can use whatever. And so we started with nickel, we'll be investigating manganese and also then carbon for a zinc air battery. But to the second part of your question, which is our business model, we decided early on that trying to build a battery company from scratch is very, very capital intensive. It also takes a lot of time to gain the trust of your customers, right? In other words, batteries are literally fundamental to everything that people use that's electronic, whether it's cars, backup systems, telecommunications, data centers, residential energy storage. People want to make sure that the battery that they're using, right, is backed up by a company that's been around and understands that. And so we thought, kind of who are we to try and establish a new battery company, because the length of time to not only establish the supply chain, but establish a brand name would be just very cost prohibitive. So we took a page from Intel, and Intel has their little Intel Inside stuck on the side of every computer, and their business model was, we're going to develop this really cool chip technology, and we'll work with a computer company to say, oh, you're doing an engineering computer or a gaming computer or a consumer computer. We have a chip for that, and we'll work with you to design the computer to take advantage of the chip, and then we'll sell you millions of chips. And that's what we're doing, is that we have the R&D engineering to go help companies, our customer, which is a battery company, build the battery using and take advantage of this technology. And then we will build millions of those chips, the anodes, and supply that to them as a drop-in component. And by the way, that's what goes on here at the MTC, is we have our R&D facility up in Richmond where engineering then develops the anodes and the cells for the application. And then down here is where we're prototyping the production processes to go do that. And I guess one last thing on us is, so who are these customers? And once again, we come back to the oldest battery in the world, which is the lead acid battery. And they have deployed over 400 gigawatts of manufacturing capability worldwide. So we've designed the battery to be built in a lead acid factory. So they would take out the lead components, right? The lead oxide and the lead components and the sulfuric acid, replace that with nickel and zinc or manganese and zinc to make a battery, but using their same equipment. And that gives them a tremendous capital advantage. To build a new lead line would cost like $25 to $35 million. And to build a single lithium line would be $150 million. And so the fact that you can build on your existing line a battery that could compete with a lithium battery by using your existing equipment and your people, you don't have to retrain them because the battery is built the same way. That's a fantastic, business value proposition for them.
Yeah. And swapping out lead grids for zinc sponges, it's got to be safer, right? And I've seen lead acid manufacturing. There's a necessary amount of safety component to that you could lax, I guess, when you're handling zinc instead. I think that's one of the things that's stands out to me when I think of what Enzinc is doing, and that's very unique. And we've definitely seen, it's a rough business, isn't it? It's starting up new battery companies. I mean, every day there's news, good and bad. And one of the big challenges, I'll often refer to it as like where the valley of death lies for batteries, is manufacturing. Is okay, you've got a cool battery, but you need someone to make your case, you need someone to make your separator. Maybe these things exist, but usually they don't. And so you're starting everything from scratch. So if you're able to leverage, especially something that we do manufacture still here in the US, like lead batteries, big advantage, I think. So I'm happy that you took the time to go into that description.
kind of going back to the sponge that you've been developing, since you've gotten the license from the U.S. Naval Research Laboratory, where have you been able to take this sponge from, getting that license to where you are today?
Great. I brought some show and tell.
Perfect.
So to put this in context, to Onas's point is it's one thing to develop a really cool technology in the lab, but it's another thing to scale it and then scale it for manufacturing, because what works in the lab at small scale, you have to be able to do this at both rate and at quality and at cost. And so to be able to do that, a tremendous amount of effort goes into doing that. And once again, that's kind of what the MTC is for, is to make sure that what we're doing can be scaled and manufactured. So, like I said, we started in 2020 at the Richmond Field Station with one lab, and then with money from the California Energy Commission, as well as from angel investors, we started making little guys this big. And so that's kind of one of our first sponges. Actually, the first ones were about half this size, and then we scaled from 10 millimeters to 20 millimeters. Ooh, big deal, right? And so we did a bunch of our testing, and then we progressively increased so that within 4 years, we're now making them this size. And so this is 80 times the area from here to here. So we've been able to make these on our line back here. These, by the way, are sized. This is 16 millimeters or 16 centimeters by 16 centimeters that go into a lead acid battery. And I don't know, way over there on that table, you can see a bunch of batteries. So those are Enzinc inside batteries. One of them is not, it's a lead acid battery, but we keep it there to show people the difference between a Enzinc inside battery and a lead battery. The difference is the lead battery, which is 6 volts at 100 amp hours, is about 30 kilos, and ours is 10, right? And that's just a prototype. We're probably going to get down to 8 to 9 in that. Anyway, so that's kind of the journey. Number one is we started off with those really small batteries, small cells, did the checking, and then grew, and we doubled the size, then doubled the size, and doubled again, and now, we have it. So that's part of the scaling operation. The other is what's going on behind me is now we transitioned late last year, all the anodes that we're building for test and for our partners that we're testing with now are built on this line. So in other words, they're no longer kind of the engineering, one-off kind of batteries. They're all built using production-like processes. And what that has given us is, of course, the ability to make these things consistently, because, in batteries, the electrodes have to be consistent throughout the cell. So we've now gotten to the point where all of the anodes, which are about 1 millimeter thick in total, including the current collector, we can produce these things, hundreds of them per day. Once again, it's a pilot line. This is not production, but we can do that now with less than 5% variation in both thickness and mass. And just yesterday, we reached another milestone where we're now at 90% yield.
Great.
And the reason that we can do that is that 4 years ago when we started, well, in 2020, we made the commitment that we would be doing this with manufacturing in parallel. We're not doing it in serial, right? Where we design something, we work on it, and then pass it to manufacturing. Manufacturing has been involved from the beginning. And so this now, when we got money from the California Energy Commission to build this facility, then that's why what we're doing is literally what goes on at the RFS, Richmond Field Station, is transferred here. This is where anode development now takes place.
Yeah, that's really great too, because one of the big challenges here is, of course, that we need this young industry, or kind of the emerging battery technologies. they need to just get to scale quickly, and so if you doing things in series is a pretty slow process. And so if you're doing something with like that kind of agility built in, I think, it's got to be scalable, and it's got to be cost effective at scale. So you can't kind of do one then the other and take too long iterating. I think engineering, manufacturing needs to guide engineering like directly.
Yeah. I mean, we kind of, our message to the engineering team, they're brilliant guys, but the idea is what comes out of that machine, that's what brings revenue to the company, right? So we have to keep that in mind, that everything we do has to, contribute to those three axes, right? Quality, performance, cost, right?
Mm-hmm. Mm-hmm.
All of
Yeah.
those three have to be balanced. I do have to say, I mean, it sounds, wow, that's really cool. You did all that in parallel. That's not without its risks, by the way.
Mm-hmm.
you know, doing that is kind of risky. You do have, you do make some mistakes where engineering and management believe that's the right thing to do. We put it down here in manufacturing and we say, oh boy, that was a big mistake, right? But if we keep manufacturing and engineering working together so that they communicate well, we do rapid testing, the classic Silicon Valley fail fast.
Yeah.
We want to do that. Our version of fail fast and software's version of fail fast are kind of an order of magnitude difference.
Yeah.
Where they can figure out something within a couple of days, it takes us a couple of months to figure out we've done something wrong. But then, of course, once you've built that learning, you can then recover and come up with, what's the next one that we need to fix that.
Mm-hmm.
Yeah.
Yeah. Yeah. Definitely agree on both of those. I couldn't help but smile that, like, yeah, failing fast is critical, especially when you're dealing with all the variables of a battery. I mean, we encounter this every day, that these are essentially black boxes with hundreds of variables inside. And so the only way you're going to understand how all these components work together and all these different variables is through iteration. One of the problems, though, is that a battery, needs to last a long time, needs to hit a lot of cycles. And so it's just, there's a part you can't speed up. You got to work in just, large, highly parallel amounts of tests. But I applaud you for striving for ways to try to fail as fast as we can. We can't rush the science in some ways, but we also can't just say batteries are slow and throw our hands up in the air.
Yeah, I mean, and that whole cycle testing thing of, you can only charge and discharge 3 or 4 times a day, and if people want 500 cycles, that's months.
Yeah. And that's our goal at Octet is to try to play a part in that by trying to iterate the electrolyte as fast as we can.
Absolutely.
try to at least figure out which things are worth those 5 months of time, because there is a part we can't speed up, or speeding it up just inevitably changes what's going on.
Absolutely.
The rate
And we
of the
do
battery
appreciate,
changes
we appreciate working with your team to get that done, because we've been operating pretty quickly, and the responsiveness of Octet has been terrific.
Oh, thank you.
Yes. Yeah, I think it's interesting too, what you say to your engineering team. It has to, come out of the manufacturing facility. It's what generates the revenue. I think what we've seen a lot in our battery industry has been, a lot of science being done, a lot of research being done, a lot of really exciting titles of articles and papers and things like that coming out. But as Onas was mentioning earlier, the valley of death comes with the manufacturing and actually getting repeatability with all of these variables in hand. So I think it is a really interesting method of development.
Yeah, I mean, and in that, Emily, I've got to, put a shout out to the California Energy Commission.
Mm-hmm.
They created a program called EPIC, which is a 5-step program that essentially helps startups, here in California, follow the process that you're talking about, which is, they have stages, and it starts off with the concept, and then a demonstration, and then test, and then bridge, which is what this facility is, to help you bridge from your engineering to manufacturing, and then ramp, which is the last one, which is to help you ramp up. They're both money, which of course is important, but also the support and the process helps us keep focused on that very thing of the objective is to deliver. And so it helps bring manufacturing to the forefront rather than, just kind of pushing it off as, oh, we'll get to that later. And you can't.
And it's I think an excellent program for having those stages. It aligns really well with what you do in battery technology. It's there have been a lot of high profile failures, bankruptcies with some very venture backed kind of new battery, not necessarily new battery chemistry, but new batteries. I mean, Northvolt kind of the headliner here, where I think there are some things that are just at odds with the way that like venture investment wants to work, not just the timelines, but the way they want to see the stages and progression. And, they want to see customer traction early. And it's hard to get that with the battery technology that has to crawl and then crawl and then crawl. And then,
Yes.
it's not like 1, 2, 3, now we're manufacturing. It's every step is a bit of a new adventure. And sometimes you have to go and kind of iterate and go back. And so a program like that, where the stages are drawn out more and there maybe isn't that kind of the pressure you get from like the investment community that's been supporting a lot of early stage battery companies, but really has to understand, if you look at some of the success stories as they stand right now in the kind of energy storage landscape in terms of new companies, they're all over a decade old. I mean, some of them are nearing 15 plus years and almost 20 years. So this requires a different level of commitment. But the problem is such an important one that the winners are going to win big, but
Yep.
they have to have that kind of patience. And so it's great that there's a we're familiar with like the SBIR programs. We've done like NSF, where there's a phase 1 and a phase 2, and that's cool. I like this 5 phases you're talking about. If it was 5, I forget. With California Energy Commission, where it's like sometimes it's not as easy as like works in the lab. All right, let's make a big one and sell it. Like sometimes there's many stages.
Yeah, just as a complimentary comment, as I mentioned, my background's aerospace engineering. I've designed missiles, aircraft, race cars, all that good stuff. Batteries are really complex. When you sit there and you go, oh, I'm an aerospace engineer, I'm a rocket scientist, I can actually say that, right? Why, yes, I am a rocket. But the fact is, you always think of them, you go to Walmart and you buy your little battery and you go, okay, how complex could that be? But the amount of engineering and electrochemistry and materials science and manufacturing to be able to turn out those little batteries, millions of them in a week, right?
Yeah.
And they all have to operate exactly the same because that's what your customer demands. Incredible amount of technology. So you're right. The time it takes to get that level of technology so that nobody actually realizes it is very difficult.
Yeah, I know. And that's the harsh truth for batteries is like they're very important, they're everywhere, and people don't want to think about them. They just need to be in the background at the ready with energy when you need it, working silently. It's a funny thing. I'll talk sometimes about how energy storage, I think in the future will kind of take a lot of the role of like petroleum. Like I think of petroleum almost like energy storage. It's like it's energy that got stored over hundreds of millions of years, and now they're like primary batteries. Every barrel of oil is like a primary battery. You get energy out of it once and it's done.
That's good.
We've been charging it since the dawn of time. But and we all know so much about the oil industry, just like the lay person knows the price of oil and a barrel of crude and all the politics that go along with it. And I think like, yeah, batteries are going to be that important in the future too. And your batteries will run your house and your grid and your car. But I still wonder if the world is ready for thinking about batteries that much, or if batteries are always just going to be like the shut up, you just work, battery. Like I don't want it. You just, if I got to think about you, there's a problem. Let's just install it. Or will people sometimes get like excited and they're like, I got these sweet batteries for my house, and I got, people are going to be buying their cars and then like, aftermarket souping them up with different batteries, like gear heads are going to become like battery heads. Will we get there, or will batteries always just be this kind of like you're working when I don't have to think about you kind of technology? I sometimes wonder.
I don't know. In the past 5 or 6 years, I've determined that there are battery groupies.
Okay.
I was so amazed when we started this. You'd say, I'm working on batteries, and people would go, oh, that's great. I'll see your stuff in Costco. But then, right, batteries started to take off, and then you'd go to parties, and people would go, oh, you're working on a battery. That's cool. When is it coming out? What does it do? So I'm not sure that we're going to get quite the fame, but there is a lot of interest. We competed many years ago and the LA Center of Innovation, and they had a bunch of VCs, right? It was kind of a competition, pitch competition for renewable energy stuff. And I just happened to draw the short straw and be the very first person to pitch, right, in front of all the VCs. So I got up there and I said, listen, Mike Burz, Enzinc, we're developing this battery. Listen, this may not sound really sexy compared to all the software guys you're going to hear from, except I just want you to know that without our batteries, they have nothing to do.
Yeah.
And we won. So
there you go.
Well, along those lines, what do you think, like the next frontiers of R&D in a field like yours, ours, like where are batteries going to go next, and what area of R&D do you think will be the next kind of big frontier?
Wow. We ourselves, I mentioned, are taking a look at alternatives in terms of the cathode materials itself and what the sponge structure enables us to do. And so the one, as an aerospace engineer, that I'm interested in is the zinc air battery.
Mm-hmm.
But the part that makes it interesting to us is, I showed you this one, which is the classic, prismatic style anode. But it turns out, because it's a sponge structure, we can actually make it curved, and not just a single planar, but two planes of curvature. So for things like putting batteries as part of the structure of a drone or a car, electric aircraft.
Michael also told us about a specific mobile storage application that Enzinc has put to work, a zinc battery-powered golf cart.
We literally took the lead acid batteries out, replaced it with 6, because it's a 36-volt golf cart with 6-volt Enzinc inside batteries. And the difference in weight is 6 times 20, 120 kilos lighter weight, which means, you can carry a lot more cargo, and it lasts 3 times as long as a lead acid battery. So we had a golf cart manufacturer come and visit, and we demonstrated this for them. They were very impressed with the zippiness because, like I said, it's a lot lighter. But then we told them, we don't even use all the space that's in the battery because we're just trying to match the lead acid battery capacity. If we wanted to fill it up so that it weighed the same, in other words, we filled all the space with our zinc and nickel material, brought it back up to 30 kilos for the battery, then your golf cart would go over 100 miles instead of 30 miles. And the engineer said, maybe we should stop calling it a golf cart. And that's kind of one of our areas of interest, right? Which is urban mobility. We're not trying to compete with long-range lithium. We think that's awesome. But for urban electric vehicles that are less than 300 kilometers, delivery vehicles, emergency vehicles, post whatever, right? You can all use that platform, for mobility. It can also be used, we did it in industrial equipment like scissor lifts and lift trucks, right? We literally just took out the lead acid, put in those batteries. We didn't have to change any electronics. The charging and stuff like that was all the same. And for residential energy storage, right? Perfect, because it doesn't catch fire at all, which, by the way, that's not just us, right? That's every zinc battery doesn't do that. But it's another attribute. If you can have something that has the energy of a lithium battery but doesn't catch fire, that's a big deal for things like data centers and telecommunications and hospitals and aircraft and marine, that you can just take out the lead acid battery, put in this battery. It fits in the same spot. You don't have to change your electronics, but it has 3 times the energy and lasts 3 times as long. We think from the user's point of view, that's a pretty good value proposition. Another thing that interests us is right now in our manufacturing, we build the battery, we like to say, the way Nabisco makes graham crackers, right? You know, they come off in sheets. But it's a sponge structure, which means that it's a random interconnected lattice. The question is, what happens if that was an ordered lattice?
Mm-hmm.
And so that then says, what happens if we could 3D print the battery itself? So people are looking at how you can use lasers, you know, to weld particles together. Right now, the laser doesn't have quite enough focus to do that, but I think we'll get there. But the objective would be, A, what happens instead of a random structure in the sponge? We could actually have an ordered and designed lattice structure for power versus energy, you know, for different applications. I would design a three-dimensional lattice structure and have the laser, the 3D printer, actually build it. And then what that means is, instead of this huge thing with all these people, I could literally have a box, and I could pour the zinc powder in. The lasers would weld it all together depending upon what you wanted, and out, you know, would come the anodes and electrodes out the other end. So it would be a totally, you know, automated process. And of course, you know, it's popular at the moment to say, ooh, and you could use AI. And we think AI to help design and control that will probably be necessary. I don't think it's mature enough right now to go do that. But the promise of being able to evaluate and analyze thousands of gigabytes of data, or help order a structure, you know, and then control the laser to design that structure, I think within the next 15 years, that'll be really cool.
Yeah, it definitely would be. I think you'd be able to achieve such, you know, high currents, such a design structure. It would be interesting to see, you know, just how much more that connectivity could bring you in terms of sheer performance.
Correct.
You know, not even, you know, even beyond just like the design and form factor kind of considerations.
Absolutely.
Yeah, cool.
And by the way, that's not just us, right? That could be other chemistries and stuff that would use that. But I think that's where I think there'll be some really big material advantages when we can start to organize the structure of the battery at that nano scale.
Yeah.
Not just look at it, but actually influence what it really is structured like.
Well, where do you think Enzinc will be in 15 years?
Oh,
Or 5? We can make it a small number if you'd rather.
You mean our plan for world domination?
Yes.
Yeah. So what our goal is to provide this kind of technology to the lead acid and the nickel cad business, because nickel cad is essentially the same thing. We like the nickel cad business because we only have to change one thing, right? We keep the nickel and we change the cadmium and we replace it. Lead acid is now two things we have to replace along with the electrolyte. So what our goal is to help the lead acid industry grow by offering this ability to use their existing equipment to offer then, you know, a high performance battery as an alternative to lead acid for applications that they are either shut out from or being squeezed out by LFP. But in the long run, like I said, we'll continue to be that supplier. But that zinc air battery, that's not something that you can build in a lead acid factory, right? That is a system in and of itself. And similar to Form Energy, at that point, I think Enzinc will actually then set up a battery manufacturing for the zinc air batteries, just because it's so specialized.
Yeah.
So we expect to have, just to put this in context, the area that we have here, the MTC, is going to be our center of excellence. So this will be the anode manufacturing center of excellence. And we'll have 3 lines in here. This one behind me will become the process development line. Then we'll have a process, another line, which is strictly process validation. And the third is process qualification before it gets sent out. And then we expect to have satellite manufacturing, in which issues that they have are brought here, we solve them, we send that back out. And that's kind of a core model that our director of manufacturing, Lynn Schluter, is working on. She comes to us with about 20 years of manufacturing at Dow, and that's kind of how Dow does it, right? They're able to maintain their quality across all their divisions because of that center of excellence that makes sure that everybody's using the same process and that problems that are identified can be solved and then the solution spread out to everybody. So that's where we see ourselves in about 10 to 15 years. Distributed manufacturing and a separate organization for zinc air batteries.
Yeah, very exciting.
Thank you. By the way, one other thing that we didn't talk about, and I just want to make sure we throw that in there, is because the battery is built like a lead acid battery, you can recycle it the same way you recycle a lead acid battery. So whereas lithium, they have some really, really fantastic compounds and things to make the battery do as possible, but trying to economically recycle it is very expensive and very difficult. Whereas this one, the lead acid industry, which has like a 99% recycle capability, has figured out how to do this very cost effectively. And since we built the battery, and it's really simple, just like lead acid, it's nickel and it's zinc and it's some separator and it's a plastic box and it's some potassium hydroxide, which is kind of like fancy Drano. You can recycle this thing just the way you do a lead acid battery. So it fits everything. It fits the ethos of the company, right? If we're going to be developing a battery, to support the renewable energy business and industry, you want to make sure that how it's being built, how it's being used, and how it's end of life all fits, the circular economy. Mm-hmm. So we've done everything to where our manufacturing processes, we've removed everything that's toxic. So everything we use to make the battery, like the emulsion and stuff, is food grade material. Zinc, of course, is zinc. And then the way in which it gets built and the way in which it gets, even the adhesive we use are kind of, non-toxic, recyclable. And so when it gets to the end of life, you can take it apart, recycle it, and turn it back into batteries or something else. And we think that's important.
Yeah, I think that's something that excites me about the aqueous battery industry is many of these batteries that are being manufactured or starting to be manufactured, they already have in mind what the recycling process looks like rather than, oh, we have all of these batteries now. What are we going to do with them? It's we're manufacturing something. How can we make this as efficient as possible? Use it at the end of life, reuse it, and push the circular economy forward.
Absolutely.
And I think the message is really strong too, that we realize we're in a big competition with Chinese manufacturing of lithium ion. And we've seen through, again, bringing up the specter of Northvolt here, but that it's hard to try to outdo them just playing the same game. They're excellent at it and they're way ahead. And so what would we be doing, if we had to think of a way that U.S. manufacturing could create a new battery that has potential to be competitive in many different markets, leveraging U.S. manufacturing. I mean, it really checks a lot of those boxes. Sustainability and all these things are great, but I mean, even I'd say secondary to the idea that like setting up new manufacturing is very challenging. We don't have to do that here. You can leverage existing. It's almost like if you were to just give the lead acid battery this like massive upgrade, kind of overnight into something that like we can leverage current existing in the ground U.S. manufacturing to make a new battery that's competitive, with lithium, because everyone's gung ho about like, U.S. manufacturing and diverse supply chain. It's a fun thing to say. It's a nice thing to dream about, but I mean, starting up from scratch is very, very, very challenging. And so avoiding all that, I think is.
And to that point, Onas, a couple of months ago, we presented at BCI, Battery Council International, the large organization that represents the lead acid industry. And we presented at one of their technical sessions on how you can convert your plant, what it means for you, both in terms of the battery itself and the economics. And we've now got 8 companies have expressed interest We've signed NDAs with about 6 of them, and we're hoping then to do demonstrations with them. So there is interest from the lead acid world on, does this make sense for them?
Well, that's a wrap on today's conversation. Thanks to Michael Burz, CEO, President, and co-founder of Enzinc, for joining us. And thanks to you for tuning in to Aqueous Energy, the show featuring pioneers shaping the next wave of aqueous battery technology.
If you like what you heard, please be sure to like, subscribe, and forward to a colleague who might find it fascinating.
Aqueous Energy is a production of Octet Scientific, a company helping aqueous energy innovators deliver their most competitive batteries yet. We've helped companies boost capacity 20%, increase efficiency 10%, and have doubled their operating life, all without any model rebuilds required.
Want to learn more? Head to the link in our show notes to visit Octet Scientific online.
Thanks for joining us, and we'll see you again in the next episode.